first for the invitation. It's always a pleasure to be back to Perimeter. In fact, this is already my third or fourth time, and I'm glad that I came back. So today I'm going to talk about some of the things I have been thinking about for the past couple of years, which is about boundaries. And defects, which in this case is like a walls, domain walls in 4D n equal 4 Superfield. And this is the working which is going on with my excellent collaborators, Aki Hashimoto and Peter Oyan, which will hopefully come out soon. So as the title shows, what I'm going to discuss is about the boundary conditions and domain walls in 4D n equal 4 supersymmetric gamma series. So there are two viewpoints you can take. One is the bulk viewpoint, and another is the boundary viewpoint. So from the viewpoint of the bulk, I would say that it's about boundary conditions of domain walls. So I have 4D n equal 4 supersymmetric gammas in the bulk. And let's say I have the flat space, so R3, 1, or R3, 1 times the half line. So let's call this direction y for some concreteness. And then there is a boundary condition at y equal to 0, something three-dimensional. And then there are some boundary conditions which you can put on. And this is what I mean by a boundary. Or you could consider the walls, which is not much different from this. So you could have 4D n equal 4 and the wall, domain wall inside. So it's 4D n equal 4, again 4D n equal 4. And well, actually, these two situations are not much different. So you can think of, by using the usual folding trick, you can think of this domain wall as a boundary condition. So let's call this theory T1, for example, and call this theory T2. And this is the same as having a single boundary condition for a product of two series, T1 and T2. I put the bar here because there is orientation reversal. So there is some boundary condition. So this is the situation. And this is a domain wall, so it's certain defect. And people have thought about various defects, well, including the people here. A lot of people have thought about various defects in supersymmetric gauge series, especially those preserving certain fraction of supersymmetry. So I call this BPS, boundaries and domain walls. And then they were useful for analyzing, to learn about the dynamics of the bulk theory itself, which in this case is 4D n equal 4. And also, not just about a single theory. So you could take various different theories here and there. So the theory here and the theory there could be different. So that's a trivial point to make. But the point is that this defect is codimension 1. So it divides the region into two. So you could have one theory here and another theory, so different theory, which you cannot do in codimension 2 and higher. So if you have a surface defect, you can always go around. So you can always have the same theory. But here, we have two different theories. So this domain wall can be thought of as a sort of a morphism between this theory 1 and theory 2. And in my case, I'm going to specialize to 4D n equal 4. But I will have a situation where, say, gauge group is UN1, for example. Let's do it large N1, or large N1, and gauge group UN2, for example. So there could be such boundary conditions. Now, well, so these are the boundary conditions. And of course, I should first say that the boundary condition itself could be huge. But that's, at first, maybe a little bit, beyond the imagination. But first of all, it's not, well, first of all, if you have a boundary condition. So what I mean here, first of all, is that I have either Dirichlet or Neumann boundary conditions for various fields. So you just set the value of the field to 0, or some constant, or their derivative along the normal direction, which in this case third direction to 0. So Dirichlet and Neumann. So that's the most obvious boundary condition you can put on. But you can also do more complicated stuff. That's why the analysis of boundary conditions is interesting. And it's interesting because suppose, for example, there is some boundary degrees of freedom which live here. And then with certain global symmetry. So let's call the gauge group here G, for example. And then you can consider a certain three-dimensional theory with whose flavor symmetry G. So this is a gauge symmetry in the bulk. But suppose that if you have a 3D theory with flavor symmetry G, but then you can couple this boundary degrees of freedom to the bulk by gauging this flavor symmetry. So that means that if you take any three-dimensional theory with flavor symmetry G, and then you can couple it to the 4D theory by gauging. So the moduli space of the possible boundary condition is actually huge and includes three-dimensional theory with that flavor symmetry, which is indeed a huge space. Now, and of course, if you want to analyze all of that, that would be too complicated. But first of all, I want to impose the condition that it's BPS. So this boundary condition of WO preserves certain amount of supersymmetries. So for the n equal 4, there are 16 supercharges. So we can try to preserve certain amount of supersymmetry here. And first, let me make a somewhat trivial point. So you cannot try to preserve all the supersymmetries here, because if you preserve all the supersymmetries here, if you know the superalgebra, and then anti-commutator Q and Q dagger generates the rotation. So it generates the Lorentz symmetry. Whereas I have broken the Lorentz symmetry along this direction. So that means that you cannot preserve all the supersymmetries. So some of the supersymmetries should be broken at least. And here, the amount of supersymmetry preserved could be different depending on the situations. So it could be half BPS, or 3/8 BPS, quarter BPS, 1/8 BPS, depending on the amount of supersymmetry. And so if you in the counting of if there is any three-dimensional field theory, counting-wise, it preserves 3D n equal 4 and 3, 2, 1. I'm not going to consider the boundary condition which break all the supersymmetry. So these are the amount of supersymmetries preserved. And I'm going to use this supersymmetries very crucially, but not much the conformal symmetry of n equal 4. Almost nothing about the conformal symmetry for the n equal 4. So that's conceptually different from what people do in, say, conformal field theory. There you have a two-dimensional theory, and there is a one-dimensional boundary condition. And suppose that the 2D theory is CFT. And then you could try to impose the conditions which preserves roughly the half of that conformal symmetry. And that's what people do in, say, quantum dots and application of CFT to theories with boundaries, like what Carly has been working on. So in that case, the conformal symmetry was crucial. But here, I'm not going to use the conformal symmetry, but just rely exclusively on the power of supersymmetry to analyze these boundary degrees of freedom. And so the analysis for the half BPS case, 3D n equal 4, that's been done very carefully by the paper by Davide and Edward, based on some earlier works, many earlier works, but for example, by Kronheimer on the moduli space of normal equations, which I'm more or less coming to. And mostly our paper the focus of our paper is going to the case with this supersymmetry, three-dimensional n equals 2. And of course, it's a generalization, but there are some important differences which we have to think about. Now, so far, I try to emphasize the bulk viewpoint. But as I said, there could be three-dimensional n equals 2 series. So I could emphasize the boundary viewpoint. In other words, I said that here in this setup, I just say that there is a boundary condition, and this 4D n equals 4 bulk spreads infinitely far away, or also in this case, infinitely far away. But I could try to say that I'm not really interested in 4D n equals 4 per se, but just interested in the three-dimensional theory. And from that viewpoint, this construction gives a way to construct various different 3D n equal 2 or three-dimensional series. So, okay, so scroll. I should go here. Let's go here then. Or maybe I could go here. Just stay here. Yeah, so what I can do is that instead of having just this one boundary condition, one junction condition. So I'm going to call this boundary condition. And well, this is also a boundary condition for that guy. But for concreteness, I might call this a junction condition, whose meaning is obvious. So it's a junction between two different 4D n equal 4 series. Now, what I can do is that suppose that I have many boundary conditions and junction conditions. Well, it doesn't make sense to write too many here. I wouldn't like too many right now, but then there is a Bark series. I'm not too good at writing figures, but in a situation like this. So there's a boundary condition here. There is a junction condition here, junction condition here, boundary condition here. And in the bulk, there is always 4D n equal 4. But in general, with different gauge groups. Say with UN1, UN1, UN2, UN3. And then there are certain boundary conditions which could preserve certain fractional supersymmetry. And then, well, this itself is a coupled system, 4D and 3D. But I can consider a limit where the size of the whole thing goes to 0. And think of it as a, well, so this can be regarded as a three-dimensional system, and it's in the limit where these things collapse. So everything collapses. And that defines a certain three-dimensional theory. And depending on which boundary conditions you use, you obtain a different three-dimensional equal 2 theory. So this gives rise to 3D n equal 2 theory. Or n equal 2 or certain three-dimensional theory. And well, if you only talk about half VPS boundary condition, which preserve the safe half VPS supersymmetry, this becomes 3D n equal 4. And then there are a couple of questions I could ask. Well, for example, then what are the boundary possible boundary conditions? If you impose a quarter BPS condition and what are the around BPS boundary conditions, that determines what kind of data which you could put on here. And then there are some other issues, like for example, how does the S duality so 4D equal 4 has S duality. So if you think of this as a composite system, bulk and boundary, and you apply the S duality to the whole system. And then, since it's a duality, 4D equal 4 stays the same, but it maps one boundary condition to another. And this was analyzed for half VPS case and by Davide, and also earlier paper for the Iberian case by Witten in the night, well, maybe 2000. And then, so this S duality, SL2Z duality of 4D equal 4 was related to some action on 3D theory, SL2Z action of the 3D theory. Well, so that's one story. And once you classify all the possible boundary conditions, and then there is a question of what's this precisely this theory? What's this theory? And in particular, well, in some cases, the answer to that is easy, especially if it has a brane pairization. And so can we learn about the 3D theory? And for example, I'm going to focus on the vacuum moduli space. So if this 3D theory preserves at least certain supersymmetry, it of course has certain non-trivial vacua, moduli space of vacua. And that has interesting structure. In fact, that's interesting in the sense that the vacuum moduli space of 3D n equal 2 theory is interesting for various reasons. And one is that, for example, if you learn first about supersymmetric quantum field series, you learn about moduli space of the 4D n equal 1 theory, for example. Depending on the number of flavors, things change. And first of all, 3D n equal 2 theory has a similar structure. Depending on the number of flavors, the supersymmetry might be broken or deformed moduli and things like that. So there is intricate structure. And part of that is governed by holomorphy, first of all. So 3D n equal 2 superspace is just the dimensional reduction of 4D n equal 1 superspace. So there is still holomorphy. So you can use holomorphy argument to constrain the moduli space in various ways. That's what people did in the 90s. But that's not the end of the story, because there are some parameters which break the holomorphy. And these goes by the name the real most parameters, holomorphy, and at the same time non-holomorphy. So some of the parameters, the real most parameters, they are, as the name suggests, it's a real parameter. So it's not constrained by holomorphy, and it breaks the holomorphy. So it's known that if you turn on the real mass parameters, this vacuum moduli space changes dramatically. And there is interesting phase structure because it's not holomorphic, so things might change in the codimension, real codimension 1 space. And another thing is that, well, people certainly have analyzed various these moduli space n equal 2 series using various combinations of the holomorphy and the brane configurations. But in my understanding, but not everything has been worked out in a completely clear way, first of all. And also, quite often people rely on some sort of not completely things are algorithmic. Sometimes people rely on guesswork and with various combination arguments to argue that something things are the moduli is like that. But what I want is somewhat like a poor man's approach to this problem. Namely, so suppose that, well, I have the example I have in mind, like for example, 3D n equal 2 UNC theory with NF flavors. And what's the moduli space of this theory? What are all the branches, and etc. And I want the algorithmic approach to this. And this is purely a three-dimensional problem, because this is, I said nothing about 4D. But you can realize this 3D theory from these brane configurations. And by relying on the bulk viewpoint, I could analyze that. So I'd like to approach this problem understanding the moduli space 3D theory from the bulk viewpoint. So that's what I'm going to do. So this was mostly the introductory part. So are there any questions so far? OK, so if not, let me try to explain a little bit more detail. First of all, OK, so how this approach works in practice. And well, let's see. Well, what I'm going to say itself should in principle apply to any 4D theory, 4D n equal 2, say, for example, and a half PPS condition, boundary condition there. And in fact, that was my original motivation, because people have come up with a candidate for 3D n equal 2, half boundary conditions for 4D n equal 2 in connection with the 3-manifold story. But here, I rely exclusively on the case of n equal 4. And one reason is that n equal 4 has a very simple brane realization. So this diagram actually has a very simple counterpart in terms of branes. So first of all, in order to not to complicate the story, let's first very quickly go through the case of half PPS case. And so in the half PPS case, well, there is a brane configurations, well-known brane configuration. That's the Hanani-Witten. In fact, that's the Hanani-Witten brane configuration. And so that's 0, 1, 2, and 3. Well, people have different conventions, but let me take this convention for a moment. And there are 3 sorts of branes, but so there are 3 conditions, but one of them is redundant. So it preserves 8 supercharges. Now, and so let's draw the y direction. Y is x3 direction. And the 3D theory lives on this D3 branes. But then it could end on various D5 and NS5. And let me take the convention that NS5 is represented by this cross circle. And line represents the line in the horizontal direction represents the NS5 brane. This is the same as Whitman notation, which is becoming popular these days. Now, and then what happens here is that I could, well, for example, I draw that there. So I could have some D3 branes. And whose numbers could be different. And they might end on some of these D5 and NS5. So some of the examples, well, if you draw a complete arbitrary one, that's not really good. But, well, for example, things like that. Yeah, and then, well, maybe this is too arbitrary. So in order not to make a mistake, let me, well, I think I'm fine with that. Say, let me, well, probably that, let me take that convention. So I could retract to this example, just to be conservative. So, for example, and then what happens, well, the idea is that, again, we have many branes here, these 3 branes here and there. And then there are various boundary conditions or junction conditions there. And each of the junction / boundary condition is represented by this D5 and NS5. But at least a priori, first of all, you could have the number of D3 branes here and the choice of D5 and NS5 for each point. And that's the defining data for 3D theory. But in this case, people have known since Hanani-Witten that there is a redundancy in this description because you can change the relative position of D5 and NS5. Sorry, I think if you've done string theory in the 90s, this is, to explain this might be a waste of time. But let's see. So, but you can, right? So D5 brane can move to cross the NS5, but then you lose this string. So you cross this, and then or the other way around. If you go the other way around, you create one string. So that's Hanani-Witten, and then you can do the same thing again, for example. And so the statement here in this case that there is an ambiguity in the order of D5 brane and NS5 branes, but you can change that, and without changing the infrared physics. And I'm emphasizing this point because the same statement doesn't hold for quarter BPS case. But anyway, so in this case, we have the graph like this. And while the interpretation at this level is not too clear, but you can look at this example, for example. And then we have a U1 gauge series. So U1, since there is one D3 brane, there is a U1 series. And there are 2 hypermultiplets. So this is 3-dimensional n equal 4, U1 with 2 flavors. And this different configuration was useful for seeing the S duality. For example, S duality exchange D5 and NS5, and you can exchange the order. And as is clear from this example, it's self mirror. Sorry, it stays the same under self S duality transformation. And that translates to the statement that there is a mirror symmetry in 3 dimensions, and this is self mirror. But anyway, the point is that if you have such brane configuration, it defines 3D n equal 4 theory in this case. Now, and then there is the ambiguity of exchanging the order of D5 and NS5. Hopefully, at this point, this is very elementary. Now, so from the viewpoint of boundary, right? So in this case, boundary condition has been classified, and basically there are a couple of things you can see already from this brane description. Although everything has a counterpart, purely fused theoretically. In other words, here in the brane analysis, I assume that the gauge group is UN, for example, and rely on that. But there is also you can also do a field theory argument, which I'll come into later. And in that analysis, applies to any gauge group, say G2 gauge group, n equal 4 with a G2 gauge group, for example. But let's see. So there are some ingredients here. One is that, as this probably even as this example shows, well, you can think of this as follows. So let's see. So you can think of this as there is some boundary condition, and there is some huge n equal 4. So there is a boundary condition here, and boundary condition there. And in this case, it turns out that that's not always the case. But in this case, it's always the boundary condition here is ending on pure D5. NS5 and D5. And so one thing to notice is that if you have some boundary conditions, there could be some non-trivial degrees of freedom which live here. So in fact, if you just look at here, you have a small interval. So there is a three-dimensional U1, n equal 4, U1, and there are two flavors because two things are coming in. So you can say that here, you have this trivial ending on 2 NS5s, but that means that there is a non-trivial boundary degrees of freedom here, which is exactly this theory. So there could be non-trivial boundary degrees of freedom. So let's call this theory V. So this is certain 3D n equal 4 theory. Now, and then there is another thing which could happen, which is that the 3 brane might end on some D5 brane. So in this case, things are simple, but the 3 brane, so in this case, it's actually just a Dirichlet condition. But the 5 brane could end on this 3 brane in a different way. So here, 3 D5 branes come in and end on a D3 brane. And people know already that what happens in this case. If you take a TDO, it's D1, D3 ending on D1. And what people know is that these things blow up and makes a funnel. And so that's right. So and what happens here is that there is the configuration of scalar fields blow up, and there are solutions to the equation. So there are 3 scalars, x1, 2, 1, 2, 3. Or maybe I could write it x4, 5, 6. 3 scalars, and they are the solutions to the norm equation. So these are norm equations. And this involves a covariant derivative. So this is a covariant derivative. So it involves a gauge field. But say you can gauge fix it, and it simply becomes a derivative. And as you can see, then it has a solution of the form that x456 goes to trace some row of t1 to 3 divided by y, where y is the coordinate here. And so let's call this y equal to 0, for example. And t1 to 3 are the generators of SU2. And the low is an embedding of SU2 to the gauge group T. And so for each such embedding, there is you can write down solution like this, local form the solution like this. And depending on how many D5 branes, so it might be the case that some of the, for example, some of the D5 might end on, etc. So depending on the number of partition of n, which in this case partition of 3. So in this case, 3 is divided into just 3. 3 divided 2 plus 1. So depending on the partitions, you have a different now such law. So this law has a graphical interpretation in terms of how which of the branes end on which. And the reason that this norm equation came in is that we have a BPS equation. So BPS equation for the bulk for this theory. So for the means that in the bulk, we just have 4D n equal 4 super m mills. So you can write on the condition that variation of the gauge is 0. And that's gamma ij, Fij is equal to 0 for certain spinner, for the supersymmetry you might want to preserve. So it has 16 supercharges, but in this case, I impose this constraint only for 8 supercharges. So there's a one-parameter choice of how to pick up these 8 supercharges. But then I could take that and impose this condition. And for ij, I use the 10-dimensional notation. So ij runs from 10 to 0 to 9. And some of the, in the 4-dimensional notation, some of these things become the commutator for the scalar field, for example. And also impose the condition that I preserve the Lorentz symmetry. So I didn't say explicitly, but I preserved I'm going to impose the Lorentz symmetry along the boundary direction. And so in fact, that's how people derive this. Well, there is a string theory realization of norm construction by going back to Diaconescu in the 90s. But this equation indeed comes from the gauge, this condition for preserving supersymmetry. And the reason I said that is that, then it becomes more or less clear what should be done for quarter BPS case too. So namely, okay, so this is more or less a sort of a very brief review of the gigantic paper of Gaut and Witten. But let's see. So if you want to go to quarter BPS, right? So you could take there are several different approaches you can take. You can first take the similar step, namely, just write down the BPS equation for 4D n equal 4, preserving instead of 8 supercharges, 4 supercharges. And then there is, in fact, the 2-parameter family for fusing that, but then I could use that, etc., and then write down the new equation, which I'm going to do afterwards. And then that gives an equation which is more general than that, and more complex structures. And also, I could use this brane picture too. And namely, in that case, we could rotate some of the branes and break supersymmetry and see what happens. And some of the things I said are saying that, for example, we could have boundary degrees of freedom, which is purely 3D n equal 2. And if you have a 3D n equal 2 theory with a gauge group G, and then you can think of it as a boundary condition by gauging. But the precise data for specifying the non-pole ending on D5 becomes slightly different. Okay, so let's go to the what equation I have. And I could do the same exercise for quarter BPS case and also for one eighth BPS case and see what equations I obtain. And the result of the analysis is like that. So, well, first of all, well, okay, so maybe I should first write down just the equation. And this equation itself is written in the paper by Neil Lambert some time ago, for example. But people haven't really appreciated the power of what's encoded in this equation. So they are really useful for understanding the moduli space. And the equation I have is like this equation. So first, let me finish writing it. Or maybe I'm proceeding too slow. Well, let's see. So x4, x5, 7, 6, 8, 5, 7. So this is the equation. And by this, I mean if you take 5, and then I should take 6 here. So this involves a lot of fields. So we have a gauge field, which I tend to write A3. And we have A4, and A5, 6, and 7, 8. And there is a sort of rotation symmetry, rotating this 5, 6, and 7, 8. And one way to explain that is that this corresponds to a configuration of D-branes where we have 0, 1, 2, 3. And D5 is 0, 1, 2, 4, 5, 6. So that was what you have here. here. But I have rotated the branes, so d5 prime, so 0, 1, 4, 7, 8. And this is the rotation. And you can convince yourself that it's still BPS, but roughly because Dirichlet-Neumann direction is 4, for example, between this d5 and d5 prime. So it breaks certain supersymmetry, but at least some of the supersymmetry remains. And people have classified, indeed, already in the 90s, what kind of various intersecting brane configurations and how much fractional supersymmetry remains. And you can, right, so you can simply take that if you like. But anyway, this is not too complicated. And then this 4, 5, 6 notation coincides with this notation. So there are, in this case, 5 scalar fields ranging from 4 to 8, 5 scalar fields. And then there is also a gauge field corresponding to the third direction. And it satisfies some certain equation. And the point is that here, the role of d5 and d5 prime is symmetric, as you see. So if you like, you can exchange the 5 with 7 and 6 and 8. That's just a 90-degree rotation. So they're on equal footing. And you can see that here. So for example, well, if you set x7 to x7 equals to x8 equals to 0, and then you are not allowing the motion in this direction, and you can check that this equation reduces to x7, 8 becomes 0, reduces to the norm equation. So in this case, we have a norm equation for 4, 5, 6. Or you could say, well, of course, you could say x5 equals to x6 equal to 0. And you have the norm equation for 4, 7, 8. So it's like more or less like a superposition of two norm equations. So we have norm equation, one norm equation, another norm equation. But since both involve the same scalar x4, they are not completely decoupled, but they interact in a complicated way. In fact, if you go to 1s BPS case, it's like a superposition of 4 norm equations instead of 2. And this equation also is more or less known in the higher dimensions. So you can think of, so this is an equation in 1 dimension, but it comes from the self-duality dimension reduction of a version of the self-duality equation in 6 dimensions, which goes by the name Dawson-Uhlebeck-Yau equation. So just as norm equation arises from dimension reduction of the instant usual self-duality equation in 4 dimensions, this arises from dimension reduction from 6 dimensions. And indeed, there are six such things. Now, so this is the equation I should solve. So if you want to analyze the moduli space of theory such and such, then what I should do is that since now I have the solution equation, so I should solve this equation on each interval. And whenever there is a boundary condition, I should impose some corresponding boundary condition there. So that should give you the moduli space. And this is purely, well, I haven't told you what the precise boundary condition I should take, but which I'm coming to later. But at least the point is that things are now easy. So, I mean, well, there are various brane configurations for, say, if you take UNC with NF flavors, there is a brane configuration for that, written in terms of D5, D5 prime, NS5, NS prime, D5. And you can just write that. And then solve the equation, solve this equation on each interval with appropriate boundary junction condition, and it gives you the moduli space. So so, and I'm going to tell you about a few examples and see how it reproduces the moduli space 3D n equal 2 theory. And while this is more or less a generalization of the what's known for 3D n equal 4, a half PPS case, there are certain interesting things happening. Because first of all, the moduli space of 3D n equal 2 series, they are quantum corrected rather dramatically as compared with 3D n equal 4. Even, for example, even some of the branches which are there could be lifted completely by quantum effects. And we are going to argue that this equation, although it's a classical equation, but this equation in combination with S-duality knows about the quantum corrected moduli space. So you can approach the quantum corrected moduli space from the classical equation and purely algorithmically. So that's what we are going to do. But of course, except that you might worry that this equation is already complicated. And in a sense, it's true. It involves a lot of scalars, and it's a one-dimensional equation, so you can solve it numerically. But it's not completely easy. But there is a nice trick to simplify the story a little bit. which is very well known mathematically. But let's see. So instead of solving this equation, first of all, the complaint I have is that, well, since I'm studying 3D equal 2 theory, the moduli space should have Kähler symmetry. Well, Kähler should be Kähler. So at least everything dimension of the moduli space should be real. If you count in real dimensions, always even. But even that is not completely clear if you solve this. Well, of course, in the end, that should come with an even number, but it's not even clear in the process of the computation. But in order to make the holomorphy, well, holomorphy was indeed an crucial ingredient in 3D equal 2. Holomorphy manifest, you could define something like this. So you could define A equals to 1 plus ix4, x equals to plus ix6, y equals x7 plus ix8. So let's define these quantities. And then these three equations become the equations. So dA plus xx dagger, yy dagger equal to 0. And we have dx equal to 0, dy equal to 0, and xy commute. Where this d is the derivative with the complexified gauge field. And we have a moduli space of this divided by the gauge group G. So this is the moduli space I'm more interested in, and this is the moduli space I want to identify with the moduli space, vacuum moduli space of the associated 3D equal 2 theory. Now there is a trick of reducing the number of equations. Namely, so I have the only dx equals dy equal to 0, and xy equal to 0, divided by plus. This is a subtle issue of stability condition. But then at the cost of that, I could complexify the gauge group. And then once you do this, so this is more or less non-mathematical, except that knowing what the stability condition is, etc., is could be a tricky issue, which resurges from time to time. But at least if you can do that, and this is a very simple equation, because this is a covariant derivative, and the covariant derivative includes this complexified gauge field. But since I have a complexified gauge group, I could gauge fix it at least pointwise. Then it simply becomes the equation that dx is equal to 0. So its x and y's are constant. So in general, these x and y's are constant matrices commuting with each other, which looks very simple. Except that there is one caveat to that. One caveat is that in some cases, well, in the case I was, okay, this is indeed very useful. So in the case I was having here, for example, so there was this num-pole. So in that case, there is a coordinate dependence explicitly. So in that case, you cannot set it to constant, but impose the appropriate condition. Namely, so for example, at the num-poles, you could have x goes like 1 over y. And in fact, since this equation is a little bit more general, I could allow, so in this case, there is just one num-pole. But since this is like a superposition of two num equations, so I could have a commuting pair of num-poles. Yes, so for example, x3, 4, 5, 6, 7, 8. And there could be a number, so let's decompose the matrix into two parts, two diagonal parts, and have the num-poles row 1, T1, or maybe, okay, so I hope people can see row 2, T2, row 1, T3, here, and then 0, and 0, 0, or maybe. And then I could have a different num-pole. Row 2, T1. So we could have a commuting num-pole, which is consistent with this equation. So this goes like, sorry, what I mean is that this goes like 1 over y. Everything goes like 1 over y. So if you look at the first, this part, only x4, 5, 6 have a num-pole. And if you look at this part, it's like a 478 has a non-pole, for example. So that singular condition is allowed. And that corresponds to the fact that here, in this case, we have a D3 brane ending on D5. But I also have D5 brane rotated in a different way, say 90 degrees or some other degrees. And then that's reflected there. So in the remaining minutes, I'd like to explain at least 1 or 2 examples where this analysis, how this analysis really gives you the quantum corrected moduli space, which I think is one of our most important findings.
Question?
Okay.
Do you have an understanding what happens when the boundary is a conformal field theory?
Boundary,
imposing.
But in general, this is a 3-dimensional theory, and it's a gauge theory. So, as it is, it has a finite gauge coupling. So it's not conformal, and there is a flow of the gauge coupling constant, simply because the gauge coupling constant is dimension full. So what I really mean by is that take the philosophy that you could study the bulk degrees of freedom on the interval, but we are interested only in the infrared limit, where these things shrink. And that's the limit where the gauge coupling constant becomes strong. And that's the limit where we start with some theory, 3-dimensional theory, and they flow to an infrared. So we are interested only in the, mostly only in the infrared limit. Except that there is even for the finite gauge coupling constant, that's also more or less under control because there is a parameter. When you solve the Neumann equations, you can say that there is an equation. You solve the equation from here to there with where the length between this and that is such and such. And if that's finite, not 0, strictly 0, it gives a finite gauge coupling constant. So the answer is that in general, its theory is not conformal, but they float. The expectation is that they float to interesting Higgs point. So let me come to some examples. So one good example, one abelian, one non-abelian. So that's the example I want to talk about. So the one example I have is 3D n equal 2 pure Yang-Mills. Well, our formalism itself applies to any gauge group, any matter. Well, as long as it has at least brane realization. So, but you're not done with the analyzing the complete cases. And in fact, there could be some interesting structure if you talk about general NC and NF. As I said, people try to explore various branches in n equal 2 series, here Coulomb branches, Higgs branches, mixed branches. But back in the 90s, they didn't have all the technology we now have there. So sometimes in some complicated examples, they just assume a little bit, there was a little bit of guesswork involved. And so we are trying to see how this more algorithmic approach, what kind of results they give, and whether there could be some missing ingredients missed in the literature in the 90s. But let's see. So for this purpose, today, let me specialize the case which we think we understand well. So that's the case of, well, let's see. First, let me write so 3D n equal 2, pure super Yang-Mills. And gauge group U2. Actually, you could do the same UN relatively easy, but let's comment on U2. And so this is flavor equal to 0. And in this case, it's known that there is an instantaneously generated superpotential which lifts the so the vacuum moduli space lifted completely. So that's actually is known even before Afric Dine-Seiberg, so it's Afric Harvey-Witten. So the vacuum moduli space lifted completely, and it's at the instanton correction, which is non-perturbative correction, is really essential. And what happens here is the following. So we could realize that this system in terms of this system where so I take my convention is that this is an S, and this dotted one. Well, I could write simply an S prime. If you ns prime, where ns prime is the one which is wrote. Okay, so I wrote the brane configuration here. Oh no, okay, maybe it's the one there. So how to put it back here? Let's see. So it's linear, so I have to compute linear and mixed, linear and mid. Okay, mid. Okay, probably if I do this. Oh, here it comes. So, right. So I didn't like ns. Okay, so I didn't like ns here, but in the original Hanani Whitney we have 798, but we could also have ns prime, 0, 1, 2, here 5, 6, 7. Well, you could also consider rotated ones, but the rotation corresponds to adding a mass to certain adjoint, and they're irrelevant in the infrared limit. Well, they change the physics, but you can get rid of that in the infrared limit we are interested in. So you can concentrate these 4 cases. And so there is ns5 and ns5 prime. So it's just a rotated one in some directions. And if you do that, you can check that it gives rise to n equal 2. So if this is both ns, it's n equal 4 super Yamils, but it's n equal 2 here in this case. Now, and then what I'm going to do is that instead of solving this, I say that I take a S duality of the whole system and have the system like this. So I might attempt to write this, d5, d5 prime. And of course, this doesn't seem to help much, except that here we have a very good understanding from Neumann equation. And well, so if you look at each of these, it's more or less the same as the half BPS condition. So here, x456 goes like 1 over y, p1 to 3. So that's the boundary condition. And here, well, since it's rotated, instead of 4, 5, 6, p1 to 3 over y minus L, where I set this to be y equal to 0 and y equal to L. So you just try to look for the solution of this equation with such and such singularity. There is no singularity in the middle. We just have the singularity here and there. And the answer is, short answer is that in the end, there is no solution, which is consistent with the fact that the vacuum is lifted completely by non-perturbative effect. And here, so well, let's see, if this were a D5, you can solve this Neumann equation in terms of Jacobi functions. And roughly what you can do, imagine, is that you have a numpole here, sorry, you have a funnel here, and you have a funnel, another funnel here, and try to superimpose. But these funnels spread in different directions. So if you have a funnel in certain direction, there is a tail which goes like this, and that makes things consistent with this boundary condition here. That's a rough intuition, but the point is that at least there is no solution. And the only comment I have is that, right, so if this, as the rough explanation shows, that if you keep these things farther and farther away, you could construct a solution, which becomes better and better. And that's related to the fact that the gauge coupling constant becomes 0, so the instant of potential becomes more and more smaller and smaller. So in this case, you just end up reproducing something saying that there is no solution. So maybe you are not too excited, except that here already, what's interesting is that this is a classical equation, but knows about the quantum corrective moduli space. So let's go to another example. So another Abelian example for simplicity. So example 2. So n equal 1, n equal 2, U1 theory. So it's SQED with NF equals to 1. And here it's known that the vacuum moduli space is also corrected. So what I mean is that there is a vector. So here I have a vector multiplet and the two color mods for phi plus phi minus. It's charge plus 1 minus 1. So that's what I mean by variable is equal to 1. And then people have analyzed the moduli space. And well, the moduli space, there is, first of all, the Higgs branch. Well, the Higgs branch is the branch where these things take values. And the vacuum moduli space should be parameterized by gauge invariant objects. So not just these things per se, but the product of these two. So product of scalar field first. So this is a gauge invariant because it has charge plus and minus 1. So this meson parameterizes the Higgs branch. Now, so it's complex dimensional 1. But there is also a Coulomb branch. And well, let's see. So and then there is a symmetry, Freiberg symmetry. So this is a gauge. And this is the Freiberg symmetry. Press 1. And it's charged under Freiberg symmetry. So what about the Coulomb branch? So in the Coulomb branch, well, first of all, there is a vector superfield. So in 3 dimensions, in the vector superfield, we have gauge field and third component gauge field, sigma, a joint scalar, which comes from the dimension reduction for 4D n equal 1, if you like. And then there is an auxiliary field, and then lambda bar. So this was the mother content. But the point is that there is a sigma here. And in 3 dimensions, you can dualize this gauge field to a periodic scalar. So this is a dual photon. And this is periodic with the period given by coupling squared. And then there is a natural variable for parameterizing the Coulomb branch. That's this monopole operator. Well, I'm using the same B. Well, let's say B hat, B tilde. And that's given by gamma plus I gamma plus sigma divided by G squared. And so the periodicity naturally is absorbed into this definition. So this is the monopole operator. And then here there is a symmetry which shifts this dual photon by some constant. That's known as the topological U1 symmetry. So it's charged under U1J. And as you can see from this, it looks like a cylinder. So there is a cylindrical direction gamma, and there is a direction transverse to that sigma. And this is just more or less like a complex plane or cone. But this is not the end of the story because there are quantum corrections. And in fact, you can see that there should be quantum corrections because, for example, here, well, first of all, everything, this Higgs branch and Coulomb branch should merge at the point where all the fields have 0. So they should make a contact. They should touch at some point. But that should really be a point. And you cannot do that because here, there is always a non-trivial action of U1J. There is no fixed point action. Whereas if this one and that one merges, there should be a fixed point. And the only way that's possible is that this is modified quantum mechanically to the things like this, where this is sigma equal to 0. And then there is another Higgs branch coming in from here, which lifts this. So this is a quantum correction. And I went into a little, so this is a well-known story in the 90s, but I went into this a little bit to show that the fact that we have 3 branches comes only after taking quantum corrections into account. So how does this come out from the Neumann equation analysis? Okay, maybe I could, perhaps I want to keep this equation. And, in fact, this is the equation I might want to use. Okay, so realizing the abelian theory is easy. So we could have NS5 and upending of NS5 prime and D5 prime, D prime, NS prime, NS. And it's one of the simplest examples. We just have a U1 theory here, and it was one Freiberg, simply because there is one. And if you like, you can put it back to here by using Hanani-Witten. So what does it mean to solve this equation here? So first of all, let me enlarge this a little bit. And so I'm going to solve this equation. And in this case, everything is abelian. So this x and y are simply constant. Very simple. Every x1 is constant. So let's call this region 1 and 2. And here we have the boundary condition from NS and D5. So I should discuss the boundary conditions there. So here, so we have in each of the regions, there is a 1 by 1 matrix. So let's call this x1, x2, y1, y2. These are 1 by 1 matrices. If you do more complicated ones, they become the n by n matrix. But here, in this case, it's really a number. And now on this NS5 end, I impose the appropriate boundary condition, it turns out, is that yi equal to 0, or at least a number. If you change it to some number, that becomes a mass parameter. But let's see. So to make things simple, let's call it 0. Right. So then there is no constraint on xi on this side. So that's one boundary condition. And here, so we have d prime. And here, we have the similar thing. So it's a d prime. And here, again, have the condition that n2, y2 is equal to 0. So maybe, to make things clear, so I mean, for example, d5 prime, the transpose direction 5 and, okay, but let's see. So anyway, so sure. So it turns out the boundary condition is here. And now what's the correct boundary condition for that? And it turns out that the correct boundary condition here is that y2 is related to y1 plus qq tilde. Well, in general, it's replaced by the condition that the jump is rank 1. This is stated in Gato-Witten, if you like. Or actually, this goes back to the old literature of the Neumann equations, which more or less known. And then there's extra constraint that xiq equals to q tilde xi equal to 0. And in the Gato-Witten analysis, that was half PPS. So this only y in here is important. But here we have to take this condition into account. And we can derive this condition by working out the coupling of the boundary degrees of freedom to the bulk using the superspace formalism by De Wolfe, Oguri, et al., for example. And I think we found that this is the correct condition. So here, in this case, it's simple. Things are very simple. So we have a constant 1 by matrices, and we just have this constraint. And since y1 and y2 are 0, we have the constraint that qq tilde is equal to 0. So in the end, we have three equations here and that. And that can be derived from a single superpotential, which is that w equals to xi qq tilde. And there are 3 branches, and that 3 branches corresponds to the 3 branches here. And so this is our simplest example. And you might have the impression that this boundary condition might be cooked up for this specific purpose, but it's not. We do have a derivation, and we use the same constraint, same boundary condition, junction condition for all the cases, for all the UN Weaver gauge series and things like that. And that seems to give this modular space. So since time is up, I should finish here. But the point, at least the point is that so people have been interested in the 90s about trying to analyze the modular space 3D n equal 2 series. But one viewpoint is that instead of seeing that, you can think of it as a 4D n equal 4 series interval. In fact, that's a very special case of the compact. You can think of it as a 4D n equal 4 series compact final interval, which could be lifted to 5D n equal 2 compact final on a cylinder, for example. So that's a particular case of the M5 brane compactations, if you like. But you can look at the problem that way, and then, so of course the problem is more or less equivalent between bulk and boundary. But if you take a bulk viewpoint, there is just a classical equation, and that seems to know about at least the complex structure and the dimension of the modular space of quantum corrected 3D n equal 2 series. So I think it's a good idea to try to revisit this old problem 3D n equal 4 somewhat algorithmically from this approach. And that's what we are doing. So let me finish here, and thank you for listening.
Are there any questions? If not, let's thank Masahito again.
Okay.